Looking at the graphs of polynomials, there are a couple restrictions that we have to place before we can start looking at the graph so we know what is a polynomial and what is not. By definition, graphs of polynomials must be smooth and continuous. Smooth and continuous. So a typical polynomial might look like that. That would be a cubic function. We've already seen those graphs. That would be the graph of a polynomial. It's smooth, it's continuous, so he's a poly. If I had a graph like this that came up and jumped and went like that, he would not be a polynomial because he's not continuous. Or if I had a graph like this that came down and then went back up, even though it's continuous, it has this sharp corner down here, so he would not be a polynomial. He's not what we call smooth. So he's not a poly. So there cannot be discontinuity, so they cannot be discontinuous, or have sharp corners. And the sharp corners are called cusps. Not that you need to know that, just a little bit of extra math knowledge for today. So there's some basic ground rules, but more specifically, and more importantly, whenever I look at the graphs of polynomials, they're going to fall into one of two categories. They're either going to be an even degree, remember the degree is just the largest power, or they're going to be an odd degree. And there's a distinct difference between what these graphs look like. So going back to our parent functions, we have x squared and over here x to the third. I'm going to sketch these. For x squared, I know he comes down, he hits at 0, 0, and he goes back up. Whereas x to the third starts down there, passes through 0, 0 at its point of inflection, and goes up to infinity. So if I look at these two graphs, I can start to get the idea of the difference between the two functions, just looking at the end behavior. For the even degree, for the x squared, it's up on both ends, and for the x to the third, it's down on one end, up on the other. And if I reflect the x squared, I see that it still holds. With the end behavior, both directions are going the same direction. And if I look at the x to the third, and I reflect him, it still is going to be opposite end behavior. So I have same end behavior, opposite end behavior. If I come down and look at x squared, x to the fourth, x to the sixth, whenever I start to graph these, you can just kind of believe me on these, or you can look them up. X squared passes down through the origin like that. He's a little more symmetric than what I just drew, but that's okay. That's x squared. If I go to x to the fourth, I take it up a step, he's going to look pretty much exactly like that function. He's just going to be skinnier. Going to be skinnier than x squared. He's still going to pass through 0, 0. X to the third is going to come down, pass through 0, 0, and he's going to be even skinnier, the x to the sixth here, than the x to the fourth or the x squared. So as the power increases for even functions, it just gets skinnier, but it still has that same end behavior. So it's same end behavior. As opposed to the odd degree polynomials. So I have my x to the third. We've seen his parent graph. If I take it up a step, x to the fifth still goes through the origin. He's just going to be skinnier or grow faster. So there's x to the fifth. Take it up another step, I have x to the seventh. And it's going to get closer and closer and closer to looking like a vertical line. But the key here again is that everything that's an odd exponent in terms of degree is going to have opposite end behavior. So let me get rid of that odd. Let's say opposite. There we go. End behavior. So anytime we look at a polynomial, we're first going to determine what its end behavior looks like based on the degree, either even or odd. So a little chart, not worth memorizing, but worth looking at. Whenever I look at it, if it's even degree, Remember, his representative is x squared. I have a positive, even, it's going to be up, up. Just think about positive x squared. A negative even is going to be down, down. I'm not going to take the time to write out limit notation for this. It would convey the same idea, but I want this to go quickly. For odd, positive, think x to the third. He's down, up. And for negative, reflected, it's going to be up, down. And I'm referring to those things left to right as I go. So the more we do this, the easier that'll get. It's not necessary to memorize the chart, but just think about x squared and x to the third, and that'll get you a good idea of what's going on. So looking at some examples here, we want the degree, the leading coefficient, and then the end behavior. So I'm going to go in that order. And for the first one, degree is going to be 3 because of the third power up there. Leading coefficient, in this case, I only care if it's positive or negative. So a positive degree 3 is going to be what I'd say down, up for my end behavior. I don't really care what's happening in the middle of the graph. I just know that on the left it's down and on the right it's up. For my next one, I have a degree 2. I have a negative leading coefficient in that negative 4 right there. So a reflected quadratic is down, down. When I get to the next one, I have an odd degree, in this case 5. So I know that the end behavior has to be opposite. I have a negative leading coefficient, so that means it's left up, right down. He's going to have the same end behavior as a reflected cubic. The middle will be different, but the end behavior is still the same. For number 4, we're going to apply some of the skills we developed earlier. Looking at the degree, I've got a first power, a first power, and a first power. So that's saying degree 3, once I would FOIL it all out. The leading coefficient is going to be 2 times 3 times 1, which I know is 6, but all I really care about is the fact that it's positive. It's positive. That's what matters to me. So positive degree 3 is going to be just like a regular cubic. It's going to be down, up. Opposite because of the odd degree, and it's going to be like the cubic parent because it's positive. Lastly here, I have degree, 3, and then 2 would be 5, and 1 more would be 6. So the end behavior has to be the same. They're both pointing in the same direction. And in this case, I have 3 times 3 times 3, which is a positive number, a 1, which is positive, and a negative 2, which is going to make the whole thing negative. If you want to multiply it all out, you can get the number, but it's going to be negative. So a negative degree 6 is reflected even, so it's down, down, reflected even. They both point the same direction. So we can get an idea of what these graphs look like on the far left and the far right, but we still don't know what the middle of the graphs look like. And that's where we're going to bring in this idea of turns. Turns are going to start to help us determine what the middle of a graph looks like. By definition, we're just going to refer to a turn as an extrema. So a max or a min. Every max or min I'm going to call a turn in my graph. And if I look at a very straightforward example here of a quadratic, I call it a turn because I am changing from increasing, right there, to decreasing, or vice versa if it's a minimum. So I'm turning the graph from increasing to decreasing. That's why I refer to my extrema as turns. So if I look at my examples down here, I want a degree 3 polynomial that has 2 turns, or it has 2 extrema. So degree 3 means I have opposite end behavior. One's down and one's up. It could be reflected in this case, but I'm just going to keep it normal. So I'm going to go ahead and just put my end behavior on my graph. And as I trace the rest of my graph out, I have to turn twice. So I'm going to come up and I'm going to turn. So there's 1 turn right there. So I'm coming back down. That means I need to turn again. Right there, there's a minimum. And that takes me right up toward where my end behavior was. So I have a degree 3 polynomial. I know it's degree 3 because the end behavior is opposite. And it has 2 turns because there's a local max and a local min. For a degree 4 would be both pointing in the same direction. I'm going to go up, up, since it doesn't say anything about reflected. And I need to turn 3 times. So as I'm coming down, the first turn would take me back up. The second turn would have to take me back down. So there's a turn. And the third turn would take me up to meet my end behavior. So in this case, I have 2 minimums and a maximum for my degree 4 with 3 turns. For degree 7 with 3 turns, I'm going to have degree 7, which would be opposite, down, up. So I'm going to put down, up, and I need exactly 3 turns. So as I start to come up, my first turn is going to take me back down. My second turn is going to take me back up. And then my third turn is going to take me back down. And that's where I run into an issue, a big issue, because I can't meet up with my end behavior because he's pointing down. So in this case, I can realize that this whole example here is not possible. It is impossible to have a degree 7 with 3 turns, and we'll define a little bit later as to what some of the requirements are for turns. You can't have a degree 7 with 3 turns. Last example quickly, just to see a whole bunch of turns. Degree 6 would be up, up. Has to be the same end behavior, so he's going to be up on both sides. I need 5 turns, so I'm just going to start turning. I get 1, 2, 3, 4, and 5. Takes me back up. So I can count them here too, just to make sure. 1, 2, 3, 4, and 5. So the general rule for turns, if you notice with all of these examples, is that an odd degree polynomial must have an even number of turns. If it's odd degree, it has to have an even number of turns so that the end behavior works out. Or if it's an even degree polynomial, it has to have an odd number of turns. Even degree polynomial has to have an odd number of turns. So that's one general rule, just so we can get some basis for what the turns could be. And then there's also another rule, kind of a bigger rule. The maximum number of turns you can have is 1 less than the degree of the polynomial. And this is maximum number of turns. So if I had, for example, a degree, let's say 10 polynomial, and I'm looking at turns, the most turns I could have is 9. And notice how a 10th degree polynomial has an odd number of turns. But just because it's the most doesn't mean it has to have 9. It could also have 7, 5, 3, or 1. It can have any of those odd number of turns, but the maximum is 9. Same idea. If I look at maybe a 5th degree polynomial, the maximum number of turns it can have is 4, 1 less than the degree. But it could also have 2 turns, or it could have 0 turns. And down below here, when we do our practice and our examples, we're going to see what 0 turns looks like. So these general rules together give us an idea of what the possible number of turns are. The maximum is 1 less than the degree, and then from there you count down by either even or odd, depending on what the degree is and how many turns you can have. We'll look at a couple examples in the next short video, and then that'll be our introduction to polynomials.